I'm going to look at the first part of bonding in this video. So we will look at ionic and metallic bonding first. Before we totally jump into this, we just want to make sure that we understand what a bond is. So a bond is anything that holds atoms together. So it's some form of mutual attraction that holds atoms together. And there are three types: ionic, metallic, and covalent. And we will go through all three, but you can see them here in picture form. An ionic bond is when you have a transfer of electrons. A covalent bond is when you have a sharing of electrons. And a metallic bond here in the center is when you have these free floating valence electrons, which we will look at. So it's all about the differences in electronegativity, which determine the bond type. So if you remember, electronegativity is an element's ability to attract electrons toward itself. So depending on whether a particular element wants electrons or doesn't want electrons is going to determine the type of bond that forms. Before we move on, I just want to make sure you understand what an electrostatic attraction is. This appeared on an AP exam, and some people were a little confused because of the wording. Anytime you see electrostatic attraction, that's just talking about two substances having different charges, and there's an attraction between the opposite charges. All right, so there's some type of electrical attraction, essentially, like a positive and a negative are near each other. So this is what allows the atoms to actually bond. So if it's an ionic bond, you have the positive and the negative coming together and they're attracting to each other. That's forming the bond. Or in a covalent, you have the positive nuclei being attracted to the shared electrons. The key is if you ever see electrostatic attraction, just understand that there's some form of opposite charges that are holding two things together. So ionic bonds here, when you have a transfer of electrons between atoms, literally one element in the bond doesn't want the electrons and the other element wants them. So there's a transfer taking place. If you look at this picture here with sodium and chlorine, you can see sodium would have one valence electron that he wants to get rid of. He's a metal, he's going to form a plus charge, and chlorine has seven valence electrons, so he wants one valence electron. So literally, sodium sends that valence electron to chlorine. Sodium becomes positive because he lost an electron. Chlorine becomes minus because he gained an electron. And that opposite charge, those opposite charges that form, bring those two atoms together and make them stuck like glue. Okay, an ionic bond is the strongest of the bonds we're going to look at. So remember, ionic bonds, transfer of electrons between a metal and a nonmetal. All right, and then a formula unit is just when you write the overall formula for an ionic compound. It's basically the lowest whole number ratio for the metal and the nonmetal that make each of them happy. So there is actually a way to show this ionic bond forming when one element transfers electrons to another. So I'm going to walk you through that in a minute, but the steps are here if you want to pause and look at them. But I think it's easier when I actually show you a couple examples here for you to get a good idea. But the basic gist is you would just show the electrons transferring using arrows, and then you make sure you pay attention to the charge on each, and you write the overall formula unit. And this has to continue until every element in your ionic bond is essentially happy and has the number of valence electrons that they want. Okay, so as I said, it's easier to do these just jumping right in and doing examples. So we want to show the ionic bond that would take place here for sodium and chlorine. And we're going to show the transfer. I'm going to show you everything you need here to get these right. So the first thing you do is you write the dot structure for each element. So we've done dot structures already earlier in the course. So we'll start with sodium. All right, so the dot structure for sodium, you'd put the symbol for sodium, so Na, and you look up on the periodic table how many valence electrons does sodium have. He's in the 1A column, so sodium has one valence electron. All right, do the same thing for chlorine. Chlorine is Cl. All right, so chlorine is in the 7A column. Chlorine has seven valence electrons. So remember, one on each side until you're forced to pair up. So if he has seven, there's going to be one side that just has one. All right, it doesn't matter which side. All right, so then you always look at this and say, okay, who wants to lose? Who wants to gain? All right, so just remember here, metals always want to lose. All right, and non-metals want to gain. So in this case, the sodium wants to lose his electron and chlorine wants to gain. All right, so you use the arrow to show the transfer, show the ionic bond. So this electron from sodium will go to an empty space there on the chlorine. All right, but when this happens, sodium has now lost one electron. All right, that's losing a 1 minus. All right, every electron is 1 minus. So sodium now becomes 1 plus. All right, and you have to show that because that indicates that he is happy essentially. He has that noble gas configuration that he wants. But on the other hand, chlorine has gained one electron, so now chlorine is 1 minus. You have to show those charges to indicate that the transfer took place. All right, when this takes place though, everybody in this picture is now happy. Sodium has lost the electron that he wanted to lose. Chlorine gained the electron that he wanted to gain. So everybody in this picture is good. So the last thing you would do is you'd write the formula unit for the compound that forms. So you always write the metal first, sodium, Na, and then you count in your picture how many sodiums were needed. All right, we only drew one, so it's just one sodium, but you don't put the one. And then you say, okay, the nonmetal goes second, chlorine. How many chlorines did you have? There's just one, so you don't put the number. So the formula unit for this compound would be NaCl. It takes one Na, one Cl in order to make the transfer take place and each element in this ionic bond to be happy or have that noble gas configuration. So this one was pretty easy. So now we're going to try another example here, one that's a little bit more fun. So we're going to do the same thing, but we're going to do calcium and phosphorus. All right, but the same steps here you need to follow. So the first thing you do is you draw the dot structure for each element. So I'll start with calcium. All right, so calcium is Ca, and it's in the 2A column, so it has 2 valence electrons. 1, 2. All right, and then we have phosphorus. Phosphorus here is in the 5A, so he's got 5 valence electrons. All right, remember it's going to have one on each side before it's forced to pair, so it will just have one side that has 2. All right, and now the transfer is going to take place. The metal always loses, the non-metal always gains. But in this example, calcium needs to get rid of 2. All right, and phosphorus wants to accept 3 because phosphorus just has 5, so he wants 3 more in order to get 8. So calcium will send his valence electrons to an empty space on the phosphorus. All right, so at this point, when you transfer those 2 electrons from the calcium to the phosphorus, calcium has lost both of the electrons that he wanted to. So he lost 2 electrons, calcium is happy, and calcium now has a 2 plus charge, and you must show that, okay, because calcium lost 2 electrons. But right now, phosphorus is not happy. Phosphorus is still missing one of the electrons that he needs here in order to get that noble gas configuration. He wants one more. But at this point, this calcium here is tapped out. Okay, he has no more electrons to give. So the only way we can make phosphorus happy is if there is another calcium. All right, so remember, if this was taking place, there would potentially be millions of these atoms available, so another calcium just comes in. But every calcium comes in with 2 valence electrons. Even though phosphorus needs one more, every calcium comes in with 2. Okay, so calcium will send one of his electrons to the empty space there on the phosphorus. At this point, phosphorus has now gained 3 electrons. Look at the picture. There are 3 electrons going to the phosphorus. He is now happy, and he has a 3 minus charge. Remember, you can confirm this on the periodic table. Phosphorus is in the 3 minus column. He would want to gain 3 electrons. All right, but if you notice, you can't stop here because now you have a calcium that is not happy. Okay, this calcium here at the bottom has another valence electron that he needs to get rid of. All right, he can only send it to a phosphorus, but that phosphorus is now done. So another phosphorus would come in, right? But every phosphorus would come in with 5 valence electrons. All right, so calcium now says, okay, I can send a valence electron to an empty space on the phosphorus. At this point, calcium has lost 2, so he's 2 plus. All right, phosphorus, though, has only gained 1. So phosphorus is not happy. All right, phosphorus needs 2 more valence electrons. The only place he can get is from a calcium. So another calcium has to come in, but each calcium comes in with 2 valence electrons. So one can go here, one can go there. At this point, calcium lost 2, so it's 2 plus. Phosphorus has gained 3, so 3 minus. At this point, every element in your picture is happy. Okay, there's a charge listed for all the elements. They have reached their noble gas configuration. You are done. All right, so now you're ready to write the formula unit. So you write the metal first, Ca, and they say, okay, how many Cas were needed in order to complete this ionic bond? Well, in your picture, there are 3 calciums. Okay, so there's 3 calciums, and then you write the nonmetal, phosphorus. How many did you need? You only needed 2. Okay, it's essentially symbols, charges, crisscross, but you just count the numbers that you needed in the picture here. So that would be the formula unit. This is what you would need to show in order to get full credit for one of these problems. Just an FYI, this is the longest one of these problems could go as well. 3 on one side, 2 on the other. All right, so if you start getting into this and you start needing more and more and more elements, then you know you probably missed something and did it wrong. So we can try one more example here. If you want to pause the video and try it on your own, that's fine. But I'm going to jump right in here and solve it. So we're going to do this for magnesium and chlorine. All right, so same deal. Magnesium, all right, has 2 valence electrons. All right, it's in the 2A column. And then chlorine has 7 valence electrons. All right, so you're going to have one side of the chlorine with just 1. All right, magnesium is the metal. He's going to send his electrons to chlorine. But once magnesium sends 1 electron to the chlorine, chlorine is now done, essentially. He has that magic number of 8. So chlorine is a 1 minus charge. All right, magnesium, though, is still not happy. He needs to get rid of 1 more valence electron. He can only send it to a chlorine. So another chlorine comes in, but each chlorine comes in with 7 valence electrons. So then magnesium will send his other valence electron there to the chlorine. Chlorine becomes 1 minus. Magnesium lost 2 electrons, becomes 2 plus. Every element in your picture has a charge. Everybody is happy. So now you write the formula unit. Metal's written first. There's just 1 magnesium in your picture, so it's Mg. Then the nonmetal, and there were 2. So the formula unit here for this compound would be MgCl2. All right, you need 2 chlorine for every 1 magnesium in order to complete the ionic bond, to complete the transfer of electrons. This brings us to Coulombs Law, which is a very important concept for AP. This is definitely something different that you did not see in honors, so you really need to make sure you understand this, and AP asks about this a lot. Coulombs Law is just going to help us determine the energy of an ionic bond, or the strength of an ionic bond. So there's the equation. The good news is you don't need to memorize the equation. You just need to understand the ideas and the concept behind the equation and what that means for us for the strength of an ionic bond. So if you look at the equation here, R is talking about the distance between the ions. So the size of the ions involved in an ionic bond are going to be important. So paying attention to atomic size is going to be very important. And then Q are the charges. So the charges are also going to be important. So whether it's 1 plus, 2 plus, 2 minus, so that's going to be important as well. So we're going to use this law to determine the strength here of an ionic bond, and definitely a big AP level idea. What that equation tells us about the strength of an ionic bond is this, all right? So the force of attraction between these oppositely charged particles, in an ionic bond, you have plus and a minus, that force of attraction is going to be directly proportional to the magnitude of those charges. What that means is, all right, it says first part here, greater the charges, greater the attraction. So if you have higher number charges, a 3 plus and a 2 minus, that's going to be a much greater attraction than, say, just a 2 plus and a 1 minus. All right. So the greater the charge here, the greater the attraction between the two oppositely charged particles in an ionic bond. And then it's inversely proportional to the distance between those charges. So what that means is the smaller the ions, the greater the attraction. Basically, smaller ions will allow them to get closer together. Therefore, you get a greater attraction. So it's opposite for size here. Smaller size means greater attraction, but for charges, it's proportional. Greater charge, greater attraction. All right, so yes, you do have to consider the size of the atoms here. So you might have to use your trends and pay attention, what happens, as you go across, you are going to decrease, and as you go down, the size is going to increase. Typically here, when they're giving you these problems, they're focusing on one of these and not both at the same time, meaning the sizes will be roughly the same, and you'll be looking at the charges if they're asking you kind of which is greater strength, or they'll keep them all roughly the same charge and they'll change the sizes and have you answer a question like that. So that's good news. Remember, opposite charges here are going to attract and same charges are going to repel. That's just something I wanted to remind you here. And very important to understand here that when we do calculate these strengths of the ionic bonds, it is very important you know that energy is always negative. All right, that indicates that these ions have a lower energy when they're combined rather than when they are separate. Nature prefers this lower energy state. So when these two ions in an ionic bond come together and form this attraction, the energy actually drops. And you might think that's a bad thing, but it's actually a good thing. Nature prefers a lower energy. All right, essentially, they're much happier together than they are apart. All right, so the energy is negative. All right, energy drops. So very important to understand this for Coulombs law, though. Greater the charge, greater the attraction between two ions, and then smaller size, greater the attraction. All right, so you might have to use this idea and actually, answer questions about this. But we're trying to use this to figure out the overall strength of an ionic bond and how that can apply to properties. Lattice energy is also very important here because essentially it's telling you how strong an ionic bond is. It's basically telling you how much energy you need to separate two ions. So let's look at the definition here. It says that it's the change in energy that takes place when separated gaseous ions are brought together to form an ionic compound. So it's very important to understand that lattice energy is talking about when you take the gas form of the oppositely charged ions and you bring them together. Okay, essentially lattice energy is telling you how much energy you need to separate those ions. So essentially it's telling you the strength of the ionic bond. All right, we know that ionic compounds here are going to form these solid crystal structures. We call it the crystal lattice structure. We have this alternating plus minus arrangement here. And it does depend on the overall formula unit here. But if you look at the picture, you can kind of see how the lithium in this case and the chlorine ions just kind of alternate and form this crystal lattice structure. I have seen questions asked about this structure. So it is important that you understand that ionic compounds do have this crystal lattice structure and how it would kind of be arranged in this alternating pattern of pluses and minuses. And again, this lattice energy does relate to Coulombs law because we know that greater charges have a greater attraction and smaller size have a greater attraction. So essentially, if you have greater charges and a smaller size, you have a stronger bond, which means a higher lattice energy. It's going to take more energy to separate those ions. All right, so they do relate here. If you have a stronger ionic bond according to Coulombs law, it's going to have a much higher lattice energy. It's going to take more energy to separate those ions. And you can actually use these ideas of Coulombs law and lattice energy to figure out properties here of these ionic compounds. You can compare compounds as well. So you definitely need to understand this idea of lattice energy. So again, lattice energy is just talking about the energy you need to separate the ions in an ionic bond. It's again telling you how strong that ionic bond is. So remember, if we have a smaller size, we're going to have a greater attraction. So typically, as you're closer to the top of the periodic table, you're going to have a smaller size. And as you have a greater charge, all right, typically as we go across, as the charge increases here, we're going to have a greater attraction. So greater charge, greater attraction, and smaller size, greater attraction, therefore a stronger ionic bond and a higher lattice energy. All right, it's going to take much more energy to separate the ions if the bond is stronger. This chart can actually be very useful because you can look at it and see these ideas of the smaller ions having the stronger bond and the greater charge having the stronger bond. So, for example, if you just look here at the first one, lithium plus and fluorine minus, you can see here the lattice energy associated when lithium and fluorine come together to form lithium fluoride. It's a little over 1,000. But then notice if you still have lithium, but then you have chlorine instead of fluorine, all right, remember, chlorine is further down on the periodic table. They both have the same charges still 1 plus 1 minus. So we're not looking at charge here. But notice the lattice energy drops for chlorine. And that makes sense because chlorine is a little bit bigger than fluorine. All right, smaller sizes mean a greater attraction. So it makes sense that lithium and fluorine, which have smaller sizes compared to lithium and chlorine, okay, it makes sense that the lithium and the fluorine here have the higher lattice energy because the bond is stronger because the size of the fluorine compared to the chlorine is smaller. All right, and then if you look at charges here, look what happens as we increase the charge, say beryllium 2 plus with fluorine 1 minus. You can see much higher than when it was just 1 plus 1 minus here with the lithium and the fluorine. So again, just you can analyze this table, but the ideas are important. Smaller size, greater the attraction, and greater charge, greater the attraction. All right, if you have a greater attraction, you're going to have a stronger bond and a higher lattice energy. This chart is just showing the process here of how ions come together and how we can calculate this overall energy for the bond forming. And we can even use this to calculate lattice energy if needed. The good news is AP doesn't make you go through and calculate lattice energy in this way or calculate the overall energy of the bond. But it's definitely something important to see. You may need to do this in college, so that's why I present it here to you. But it's not going to be something you're going to be expected to do on an AP exam. So if you look at this, if you remember the definition of lattice energy, it said we have to bring together gaseous ions in order to determine lattice energy here. So you notice the first thing that happens here in this process, we're trying to form lithium fluoride, is that lithium solid goes to a gas. Well, that's sublimation. If a solid goes to a gas, that's sublimation, and there's a certain energy associated with that. All right. And then we said it has to be gaseous ions. So we have lithium gas, but now we need to get it into ion form. It has to form a 1 plus. Well, if lithium gas is going to form 1 plus, it has to lose an electron. Well, losing an electron or removing an electron is called ionization energy. So there's a certain energy associated with that. So now you have the lithium ion in the gas form. It's ready to come together and form the compound. But now we need the other participant here, the fluorine, to be in the gas and the ion form. Well, if you notice here, fluorine typically exists as F2. Well, we only want one of those fluorines, all right? So basically, they look at the bond energy here, but it's only for half a mole, all right? And there's a certain amount of energy associated with breaking the bond here in the F2 molecule. And notice these energies are positive. That indicates that energy needs to be put in to do this. So it actually costs some energy here at first in order to get these ions into their proper form in order to combine. All right. Well, now that you have fluorine in the gas form, it still needs to be an ion. All right. Well, fluorine has to be a 1 minus, so fluorine has to gain an electron. Well, adding an electron is known as electron affinity. And you can see the amount of energy that is released here. Notice this is negative. When you give fluorine an electron, energy is released. Okay, so there's a certain energy change associated with that. So now you have your lithium plus in a gas form, fluorine minus in a gas form. Now you can bring them together, and that's the definition of lattice energy. When the gaseous forms of the ions come together, that's lattice energy. All right. So once you bring them together, there's a certain energy change associated with that. And notice it's a negative number because remember, they prefer to come together here rather than be apart. So energy is given off. It's a lower energy state. And in this case, the number is very high because both of these atoms have a smaller size. So they have a greater attraction here. And then this last part, this delta H, is just talking about the overall energy change that took place here. Okay, so remember, lattice energy is talking about how much energy is needed to separate the bonds, but this last part is basically like the overall kind of totaling up here. If you add up all of these amounts, all the energy it took that you had to put in, and then all the energy that you get out when they come together, you get an overall energy change. And notice it's negative, which means even though it took some energy for some of these things, like you took some energy for sublimation or it took some energy to break the bond here in the fluorine, you still get energy given off, meaning these two atoms would prefer to come together and form the bond because you're going to be in a lower energy state. So that's the basic process here of lattice energy. They could do this a little differently. You could be given the delta H, all right, and be given the other values and asked to solve for the lattice energy. That would be just, using an X here. You would add up all of these plus this is X, and it would be equal to the negative 617, and you would just solve for X. So there's a lot of things they could do here, but again, this is not something that AP is going to do. It's not even necessarily something that I would make you do here, but I do give you like a practice problem with it just to see if you understand the ideas. And it definitely is something you might have to look for and understand in college, but it definitely helps you understand what lattice energy is and the overall process, because you have to get the gaseous ions coming together in order to determine the lattice energy here. This is just another example of one of those lattice energy problems, but again, you're doing it this time for sodium chloride. So this time they don't put it in order for you. You kind of have to think through and see what you need from this table up here. But basically it's the same idea. You have to take sodium, get it into the gas form, which would be sublimation. Then you have to take sodium gas, get it into the ion form, which means it's removing an electron, which would be ionization energy, right? And then you have to split the bond between the chlorine here. So that's going to be bond energy. And then chlorine's going to have to gain an electron, which would be electron affinity. And then the last part is when those ions come together in the gaseous form, that's lattice energy. And then when you total them all up, you get an overall value, which tells you the overall change in energy when these ions come together. And notice it's negative again, meaning they prefer to come together rather than be separate. So we're in that lower energy state here. All right, so this is just another example. Again, just wanted you to see this so you would understand it. Might give you a practice problem with it, but it's not something that I usually hold you accountable for, and it's not going to be something that AP is going to hold you accountable for, but you might see it in college. So I'm just going to walk you through some basics here for ionic compounds and some of the properties. You're more than welcome to pause the video. I might go through this pretty fast, but we already know that ionic compounds are made of metals and nonmetals here. All ionic compounds are known as salts. You're used to hearing table salt just referred to as salt, but all ionic compounds are salts. And basically what happens is you take those formula units and they just repeat over and over again, and they form these nice beautifully arranged structures. Okay, so ionic compounds are very organized, very arranged. The first property of ionic compounds here are that they are very strongly bonded. Okay, think about this. Metal, non-metal, metals become positive, non-metals become minus, opposites attract. They form a really, really strong attraction here between the two ions. Okay, because they have a very strong attraction, they form these very organized structures, which we call a solid crystal lattice structure. Okay, they are beautifully arranged, regular repeating pattern, and oftentimes they do form crystals. If you look very closely at some table salt, you will see those crystals. Okay, so very organized, very stable structures for ionic compounds. Because ionic compounds have that very strong attraction between the opposite charges, they have very high melting and boiling points. Okay, the opposites are so strongly attracted to each other that these things don't really want to come apart. So you need a lot of energy here to make them melt or boil. If you look over here, all right, this is just magnesium chloride. Melting point is over 700 degrees Celsius. Boiling point is over 1400 degrees Celsius. So very high melting and boiling points. And then something interesting here, ionic compounds are typically soluble in water, so they will dissolve. But something else happens as well, okay? Not only do they dissolve, but they actually do something interesting called dissociation, okay? So when you put an ionic compound in water, they don't just dissolve, they actually separate into their ions. So if you were to take table salt, sodium chloride, and put it in water, All right, it doesn't just disappear, it actually separates into Na plus ions and Cl minus ions. And you might say, well, why does this happen? Because, you know, sodium and chlorine, they both have those opposite charges. They should want to be, stuck together like glue. Well, what happens is here, as you'll find out, water has these regions of charge. So when the Na plus comes apart from the Cl minus, the water turns and points its negative regions toward the Na plus. So he essentially becomes surrounded by negatives, so he's thrilled. And then the opposite thing happens here for chlorine. When chlorine is comes apart, he's minus, so water turns and points all the positive regions of the water toward the chlorine, so he becomes very happy because he's surrounded by positives. All right, so as long as the water is present, these ions stay apart. But then when the water disappears and evaporates, the Na plus and the Cl minus will come back together, and that's when if you see like water evaporating, you see the salt reforming, okay? So very important, ionic compounds don't just dissolve in water, they actually dissociate or literally separate into their ions. Okay, this is very important for future learning in chemistry. Another property here of ionic compounds is that they will conduct electricity, but they will only do this when they are melted or dissolved. Okay, we just talked about how when you put ionic compounds in water, they literally dissociate into their ions, into the pluses and the minuses. All right, in order to be able to conduct, you need negative charge to be able to flow. When an ionic compound is together here in the solid form, it's too orderly. Okay, the plus and the minus are stuck together, so the negative cannot flow, it cannot conduct electricity. But as soon as you melt it or put it in water, those plus and minus come apart, and this allows the negative charge to be able to flow and allows the electricity to be conducted. So very important to remember that ionic will only conduct when melted or dissolved. So the last major property of ionic compounds here is that they are extremely brittle. All right, if you hit them hard enough, they're just going to shatter into a million pieces. And if you look at your container of table salt, you will see this. All right, the little grains of salt are already in pieces. And the basic gist is that these ionic compounds have these very organized, very stable structures where the plus is, attracted to the minus and everything's perfectly aligned. So if you hit that um, compound hard enough, you essentially form light charges to come in contact with each other, which would just cause the entire structure to kind of break apart, repel, and shatter here. Okay, so ionic compounds are very brittle because of this. Now we're going to take what we know about ionic properties and lattice energy and Coulombs law and kind of bring this all together to see how we could be asked questions about this on an AP exam. All right, something very important I want to point out here, and this will apply for the entire course and for the entire AP exam. All right, when you're given a question that has multiple substances in it, you need to make sure that you are mentioning both substances in your answer. You can't just pick one substance and then focus on that substance. You kind of got to make sure you're mentioning both substances or both ions in the actual answer. All right, you got to remember to do that in order to get full points on the AP exam. All right, so it's just something you got to get used to so that you can get those full points. So right now, I have two questions here. The first one wants to know which has a stronger bond, and it gives you two choices. And then the second one wants to know which is more soluble in water, and you have two choices. So you have to take what you know here about lattice energy, Coulombs law, and properties, and bring this all together to be able to answer these questions. I would pause the video right now, come up with, explain these answers, and then when you rejoin, you'll see the fully explained answers here. So pause the video right now and try this. So here are your answers for these two questions. Let's look at the first one. We want to know which has a stronger bond. So NaCl would have a stronger bond. And the reason is, first, both of these substances here have a 1 plus combined with a 1 minus. I didn't mention the 1 minus here, but in an AP answer, you would definitely want to mention both substances have chlorine 1 minus in them, and both substances have a 1 plus cation, sodium 1 plus and potassium 1 plus. So it's not the charge that's important here, but sodium has a smaller size than potassium. All right. Remember, smaller size, greater attraction. So we're not looking at the charge here because the charges in each are both 1 plus 1 minus. Very important to mention. So it's going to come down to the size here. All right. So if the sodium has a smaller size and a greater attraction, it's going to have a higher lattice energy, therefore a stronger bond. Very important to remember, you mention all substances and ions here in order to get full points. And then the second question, the one that's more soluble in water, is going to be the sodium chloride. Again, you can see here, I mentioned that both atoms are bonded to Cl1 minus, all right? And both atoms basically have the exact same size here. Na plus and Al3 plus are going to resemble neon in terms of their size. They're isoelectronic here. So it's not going to come down to size, and it's not going to come down to the chlorine 1 minus. It's going to come down to the difference in charge here between the sodium, which is 1 plus, and the aluminum, which is 3 plus. All right. The aluminum has the greater charge, therefore the greater attraction. So if the aluminum has the greater attraction, the stronger bond, the higher lattice energy, it's not going to be as soluble. It's not going to want to come apart as easy. All right, so you see how you have to take this idea of a lattice energy and bond strength and kind of tie it in with properties here. If it has a stronger bond, it's not going to be as soluble, or it's not going to dissolve as easy. All right, so you definitely need to be able to do this, and you need to be able to explain these questions fully and mention all the substances for AP. All right, so as I said, we were also going to talk about metallic bonds in this video. Metallic bonds are not really bonds at all. These are just the attractions that allow metals to kind of be on their own, okay? People always confuse metallic bonds because they think, oh, it's a metal bonded to another metal, but no, that doesn't happen. It's not like a diatomic or anything like that. It's literally just the metal itself, okay? So what happens here is metals don't want their valence electrons. They actually want to get rid of them. So what happens in a metallic bond is that we say that there are these free floating valence electrons. Okay, so you kind of like each metal atom dumps its valence electrons and they're shared between all the different atoms. Okay, so it's easiest, think about if this was a piece of aluminum foil. It would just be aluminum, all right, but there would be multiple atoms of aluminum. So what happens here is all the nuclei of the metal want to get rid of their valence electrons. So they all kind of dump the valence electrons out here, and the valence electrons are just free to move between all the different positively charged nuclei of the aluminum. Okay, so it's just aluminum. Okay, but this is what allows a metal to exist by itself. Okay, because think about it, this metal is looking for a nonmetal. It would like to send its electrons to a nonmetal so you can form that ionic bond, but it's not available. All right, so they literally here, each atom just dumps its valence electrons, and those electrons are free to move between all the different metal atoms. Okay, so these are not ionic, all right, but they do have a lot of similar properties to ionic. And we say that these positive cations here, these positive nuclei, are floating in what we call a sea of electrons. It's not a real sea. Okay, every year I get somebody telling me that the electrons are going swimming or something like that. It's not really that. But this is what keeps metals stable and allows them to exist by themselves. They're not actually bonding to anything, despite what the name is. So basically, in a metal or in a metallic bond, all right, all these valence electrons are free to move between all the different metal atoms. Okay, so being able to move here, all right, is what leads to what we call this sea of electrons. All right, free floating valence electrons in a metallic bond. So we already know a lot of the properties of metals from previous units, but basically the reason why these properties occur is because of these free-floating valence electrons, these valence electrons that are mobile. Think about it, all right? Metals are malleable and ductile because if you hit them, all right, the valence electrons are free to move, so they would just rearrange themselves to prevent any repelling. So metals bend, they don't shatter like an ionic compound. They literally just rearrange the electrons, prevent repulsions from taking place, which allows the metal itself to be bendable rather than shattering here. But they're also conductive for this reason as well. Metals are conductive in their solid form because the electrons are free to move. They don't have to be dissolved like ionic compounds. In a solid form, a metal will conduct because those valence electrons are mobile, because they have these free floating valence electrons. So this is great because it shows you the difference between ionic and metallic here. So notice here on the left, all right, if you hit a metal, all right, because of those free floating valence electrons, they just move around, reposition themselves, and prevent the positives from repelling each other, and it allows the metal to bend rather than break. But in ionic compounds, they are so organized that if you hit them, all right, you cause like charges to come in contact with each other, and this causes a repulsion, which causes the shattering and causes ionic compounds here to be brittle. So the free-floating valence electrons in a metal allow it to kind of slide like grease, and it makes the metals bendable. The last thing we're going to talk about here are alloys. Alloys are mixtures, right? So if you think back to what mixtures are, but they're mixtures here in which one of the substances is a metal. Okay, so we might have mentioned these earlier on, but didn't call them alloys. But the basic gist is usually you mix these things, you heat them up, cool them down, and you get these alloys forming. So there's some examples there. Brass is a mixture of copper and zinc. Bronze is copper and tin, and steel is usually iron with some other things mixed in. All right, so these exist and they are created all the time here in industry for various reasons, as we're going to see. So, why do we make alloys? Well, we make alloys because they give us better properties than the metals themselves. We get much better characteristics here that we're looking for. For example, sterling silver, which is mostly silver with a little bit of copper mixed in, is harder than regular silver, but it's um, soft enough to still work with. It's going to be more durable, makes it perfect for using in jewelry. Okay, it's much better than using regular silver alone. Steel's much better than using just iron. It's going to be corrosion resistant, it's going to be hard, tough, and it's also going to be cost effective. So basically, we form these alloys to get better properties here. All right, and there is definitely more coming with alloys here in section 3. So this is just kind of the first part of alloys, and there's definitely more you need to know, but it definitely gives you an idea here, a little reminder about alloys to start. So ionic bonds are when you have a transfer of electrons, but covalent bonds are when you have a sharing of electrons. This is going to be between two nonmetals. Remember that nonmetals don't want to give up their electrons, so they're not willing to transfer, but they will share to get that magic number of 8. If you think about it, this is a way that they can have less electrons and still get happy. All right. If you look at the sharing here between these two atoms, each would want 8 electrons here in order to have that magic number. That would take 16 electrons. But by sharing a pair, they only need 14 total electrons to reach that magic number of 8, because essentially this pair here counts towards each. Uh, so these are covalent compounds or molecular compounds. They're the same thing. Remember, molecules are just these atoms that are formed with a covalent bond. You still need to know the diatomic molecules here. These are the atoms that cannot exist by themselves. So it's your hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you're dealing with oxygen, you have O2. Or if you're dealing with chlorine, it's Cl2. It cannot be by itself in nature here. So you definitely need to remember those diatomics. So an idea here that's very important for AP is this idea of bond length with these covalent compounds. So bond length is the distance where you have the energy at the minimum. This is basically the right distance where these atoms come together and the energy is at the lowest. So there's some things happening here. You got to understand when these covalent bonds are going to form, there's some good things and some bad things happening. So as these two atoms come together to form this covalent bond, two bad things are actually happening. First, you're having some electron-electron repulsions. All right, as they're coming together, the electrons are all the same charge, so they're repelling a little bit. And then the nuclei are also charged, All right, they have a positive charge, so there's this proton-proton repulsion. So as these atoms are coming together, there's kind of two things here that are kind of wanting to push them apart. However, there's one good thing that's happening. When those electrons are put between the two atoms and the covalent bond is going to form, there is a proton-electron attraction. Essentially, the nuclei of each is attracting to the electrons that you're sharing. So that's a good thing that's happening. So the basic gist is you have attractive forces and you have repulsive forces. And when the attractive forces are great enough to offset any of those repulsive forces, the energy decreases and the bond forms. Remember, we're always looking for this lower energy state. So if they were coming together here, you got to get that right moment when the attractive forces are great enough and they kind of offset those repulsive forces, the energy drops and the bond forms. So this idea of bond length and the energy dropping and being at the minimum is very important here. You need to be able to understand a graph like this as well. This is something that AP has used, put on the exams, and you have to understand what's actually taking place here. So your energy is on the y-axis, and then the distance here, the internuclear distance, is going to be on your x-axis. So basic gist is if you're trying to form a covalent compound, all right, so let's look at the one extreme. If you have two atoms trying to form a covalent compound and they're too far away, okay? So basically, if they are so far away, so the distance is very great here. That's why we're kind of further to the right. But notice the energy is basically at zero. There's no energy here between them. All right, so that's not good. They're too far apart. Well, let's look at the other extreme. What if these atoms coming together form this covalent bond are too close together? All right, so notice the distance here is much shorter. Well, if they're too close together, those repulsive forces are going to be too great and the energy is going to be too high. All right, that's why you're in the positive region here for the energy. Well, that's not what we want. We want a lowest energy here when these things are coming together. So when you get the right distance between them, notice the energy drops. You're in this lower energy state, all right? And the distance is just right. So you would have to get the bond length here from using this axis with the distance, all right? And then the energy would be determined here from the y-axis. So it's kind of like the Goldilocks effect. It's got to be just right. Too close, the energy is going to be too high. Too far, there's not going to be any real energy change. And if it's just right, that's when you get the lower energy state, which is what we want. And then you can get the bond length from that. So definitely make sure you can understand and get information from a graph like this. Here's just another example of one of those graphs. Again, if the atoms are too far apart, the energy difference is going to be zero. If they're too close together, the energy is going to be too great. We want the lowest energy possible, so it has to be when they're just right. So if you were reading the graph like this, the bond energy would be the value on the y-axis essentially here, and the bond length would be determined from your x-axis. So definitely be able to read and understand one of these graphs. A little review of the properties of covalent compounds. Remember, if you know ionic properties, these are pretty much opposite. All right, covalent are going to have low boiling and melting points. They're not usually going to conduct electricity. Typically, they're not even soluble in water, but covalent have a wide range of properties here. So some might dissolve like sugar, but then they're not going to dissociate. All right, they're not going to conduct electricity. And most of them don't actually form crystals. Most covalent compounds are liquids or gases at room temperature. But again, there are a wide variety of properties here. So something like sugar does form crystals, but this gives you a general idea of the properties of covalent. Definitely understand the difference between dissociation and dissolving. Remember, ionic compounds, the metal and nonmetal, they dissociate in water. They literally separate apart into their ions, into the pluses and the minuses, and each ion gets surrounded by water and gets stabilized essentially. So when you put something like an ionic compound like salt in water, literally the salt separates into the Na plus and Cl minus ions. All right, so that's dissociation. That's why ionic compounds conduct, because they dissociate in water and the charges can flow. But something like a covalent compound like sugar, that dissolves, but it does not separate into the ions. Each of the individual sugar molecules gets surrounded by the water, and then it dissolves, but it does not separate into the ions. That's why sugar, covalent compound here, would not conduct. There are no charges there to be able to conduct. You need to know the difference between dissociation and dissolving and what's happening with this. This is just showing you a difference here between ionic and covalent kind of on a particle level. So remember here, ionic compounds form that crystal lattice structure, that alternating kind of plus minus structure here, depending on the formula unit. And it forms these nice orderly arranged structures. So if you're looking at this here, it alternates the pluses and the minuses. So something like sodium chloride versus water, which is less organized, and you have molecules of them, you can see it's definitely not in that perfectly arranged structure here. So you got to understand these things kind of from a particle level as well. As I said, covalent compounds have a wide range of properties due to the intermolecular attractions that can form. But remember here, there are these things called network solids, which are these very, very stable structures, basically where every atom is covalently bonded to every other atom. So that makes these very stable structures. They have very high melting points, well over 1,000 degrees Celsius or higher. And basically, in order to melt one of these network solids, you have to break every single covalent bond. You're not just breaking attractions. You have to break all the bonds to get these to melt. So it takes a lot of energy. So something like a diamond or sand, which is SiO2, or SiC here. You gotta be able to identify these network solids and understand that they have very stable structures. And the reason they have high melting points is because you have to break every single covalent bond to get them to melt. You're not just breaking attractions. And that's why you see very high melting points here. So remember, a wide variety of properties in covalent compounds. Just be aware of that.